Did the Quran predict the existence of the Pulsar 1450 years ago? This is Dr. Ali Zaini. The answer is yes, and here is why.
What is the pulsar, and what makes it pulse? Pulsars are rotating neutron stars observed to have pulses of radiation at very regular intervals that typically range from milliseconds to seconds. Pulsars have very strong magnetic fields, which funnel jets of particles out along the two magnetic poles. These accelerated particles produce very powerful beams of light. It resembles a lighthouse.
The mention of the Pulsar in the Quran 1450 years ago. In chapter 86 of the Quran, verses 1 to 3, we want to pay attention to two keywords here. The first keyword is Al-Tariq, which is the knocking, something that produces knocking sound, and THAQIB, which means shining, bright, or penetrating. So we want to pay attention to the mention of these two words. The Quran says, والسماء والطارق, by the skies and the Tariq. وما أدراك ما الطارق, do you know what is Al-Tariq? النجم الثاقب, it is the Thaqib star. If the output of the radio telescope is connected to a speaker, the sound resembles the knocking sound at a steady rate, and this resembles the meaning of the word Al-Tariq, which means the knocker. Al-Thaqib means shining, bright, or penetrating, and this description should also resemble the Pulsar because it produces very powerful beams of light.
Put very briefly, a pulsar is the core of a star that has collapsed into a neutron star, but it also has some additional properties that are very important. First, these pulsars spin very rapidly. They also have very strong magnetic fields, and these magnetic fields actually produce a powerful thin beam of radio waves that shoot into space. And we can actually sometimes see this radiation beam as a repeating pulse pattern, so we'll see this blinking pattern in the sky. The magnetic fields that the star has, so our original star will have, some magnetic fields, but these magnetic fields will be compressed along with the star, resulting in some extremely powerful magnetic fields, as we have shown in this diagram. Now, these magnetic fields rotate along with the star, and as they do that, they'll actually produce a very powerful beam of radio waves that shoot out of the north and south magnetic poles of the star. Now, in general, the direction of this radio beam is not along the same axis that the pulsar is spinning on. So as this pulsar rotates, this beam of radiation will point in different directions in the sky. And I actually have a video of this. Okay, so this video shows how this radio beam will sweep across the sky as the pulsar rotates, very much like a lighthouse. So we start it going. Now, if this radio beam isn't pointing directly towards the Earth, we really don't see very much, since neutron stars don't shine like other stars. But if the neutron star is oriented in the right way and the Earth is in the right position, every time the neutron star rotates, we're going to see a little burst of radio waves for a short time. So every time this object spins around, we're going to see a blip, blip, blip pattern. And we can detect and measure this signal by using radio telescopes. And we'll talk a little bit more about the kinds of telescopes we use in future videos. At this time, we've discovered about 2,000 different pulsars within the Milky Way galaxy. And we expect that there are many more out there. We're still actively searching for new pulsars. And each one of these pulsars has a unique spin rate and radio pulse profile. So these radio pulse profiles correspond to the intensity of the radio waves that are arriving at our telescope every time the pulsar rotates. So this big spike corresponds to when the radio beam is pointed directly towards us. And we can actually listen to these pulse profiles just by taking the output of our radio telescope and hooking it up to a speaker. And I have a couple examples of this. So these pulse profiles and sound files all come from the Jodrell Bank Observatory in England. And the first pulsar we're going to listen to is B0329. Now, these pulsar names basically correspond to their location in the sky. It's the right ascension and declination, but it's not that important. So this first pulsar rotates at 1.4 rotations per second. So this is what we hear. So that repeating blip pattern is really what is happening every time this pulsar rotates. Every time it points towards the Earth, we see this little burst of radio waves. And this one rotates 1.4 times per second. So the next pulsar that we're going to look at is the crab pulsar. And this pulsar rotates 30 times per second. So here's what we hear. So if you imagine this as corresponding to this pulsar spinning, you get a sense of how fast this object would actually have to be spinning. And this really is what we get when we point a radio telescope at the Crab Nebula. We hear this very, very fast repeating pattern associated with it. So that's a medium speed pulsar. Now let's look at one of the true millisecond pulsars. So this pulsar rotates 174 times per second. It rotates so fast that we're not going to be able to hear the individual pulses. We hear it as a single tone, and here it is. So this pulsar is spinning as fast as a blender. It's every time we get one of those pulses corresponds to it rotating around once. So it's just rotating at a truly unimaginable speed. So we see these different pulsars, and each one of these pulsars is unique in its pulse profile and its rotation rate. Now, it turns out that these pulsar signals can be exceedingly stable and regular, most notably for the fastest rotating millisecond pulsars. And for some of our best pulsars, we can predict when an individual pulse is going to occur years ahead of time to within an accuracy of 100 nanoseconds, or 1/10,000,000th of a second. This incredible timing accuracy can sometimes rival that of atomic clocks on Earth, especially over long time scales. And it's this property that allows us to use the pulsar signal basically as a kind of celestial clock, and each one of these pulses is one of the ticks of that clock.